Okay, should have started. Okay, so I'm hearing myself in the background, but I don't know what's the latency on the stream. And it seems to be quite low frame rate. Okay, should have started. Okay, so I'm hearing myself in the background, but I don't know what's the latency on the stream. And it seems to be quite low frame rate. Okay, so I'm hearing myself in the background, but I don't know what's the latency on the stream. Okay, well, let's start up KiCad, maybe switch it in English. Which is done. Why do you do that, actually? Okay, so I'm hearing myself in the background, but I don't know what's the latency in the stream. Okay, well, let's start up KiCad, maybe switch it in English. Which is done. Why do you do that, actually? Okay, yeah, and so it seems that the sound of my computer is looping back in the stream, so just gonna turn that off. Maybe I can just... yeah, no, it's okay, just like this. Keeping an eye on YouTube and Discord. Right. So yeah, let's okay, so let's just show around where we were in KiCad for the proof of concept. So what I will be doing tonight is doing some advancements on the proof of concept board that we are designing for the M17 OpenHT project. And so you have on the left the schematic of the system as of now. So we will be using I don't know, okay, a nuclear board like this one. So STM32F469I-Disco if you're interested. And this will be the microprocessor running the proof of concept. And the board that we are designing is a daughter board that is going to interface with the connectors, Arduino Uno connectors on the board, and the extension connector on the nuclear board. And we are going to use that, so we are going to do the daughter board with all the radio part and the signal processing part. So we have an FPGA which will be interfacing between the MCU and then the transceiver. Of course, we have a transceiver, which is this reference right here, if you can read. And yeah, of course, we have to design a power supply stage. This can be quite finicky. If you have a bad power supply on a radio system, it can be quite annoying. So we really wanted to have a power supply design on the first stage of the proof of concept, so that we could maybe make mistakes and fix them before having a second board. So yeah, this is the power supply, and then we have the various connectors for the interface with the nuclear boards. So maybe quickly a review of where we are at. So maybe start with the power supply, which is for me was maybe the hardest part, because it turns out that switching power supplies can be quite hard to design, especially because we are on a battery powered system, which will be powered by a 2 cells lithium battery actually. So it's 7.4 volts nominal, but it can go up to 8.4 and down to 6 volts. So it turns out that there are not that many buck converters which can run with that input power supply voltages. And also these devices tend to have bad efficiency when you are at light loads, because of the switching of the MOSFETs and so on, you lose a lot of energy in that for very little of energy output. And so of course this crashes the efficiency. So the one that we have is the TI TPS 65261, yes. So it is one chip with 3 buck converters, and one is not used for now, but might be used later on, depending on what we will be designing. And so we have a first 3.3 volts, which will be used to power the MCU later on, but for this board, it's going to be used for the FPGA and the FPGA and the transceiver. So trying to have a look at the chat maybe. Yeah, okay, so 3 volts common rail, then 1.8 volt is used by the FPGA, and then you have 1 volt which is needed by the FPGA core, and this one especially needs to be noise free and ripple free. So we picked an LDO. Which has sufficiently high power supply rejection ratio. It seems that I have a bit of buffering issues, but I don't know actually if it's buffering issue from the bandwidth or from the yeah, okay. This might be related to my graphic card, which is old and saturating. Sorry. I don't know what I can try to do that. I never stream, so I don't know what are the parameters needed to improve this. Maybe Casey, you can give me a few tips. Yeah, maybe we'll try to decrease resolution. Okay, welcome back. So I will be waiting for some feedback maybe on the quality of the stream. Okay, looking better yet. Okay, and can I see the latency in the stream? Yeah, okay, it's a bit better too. Okay, and I will move maybe my head right here so that I'm not just under the M17 logo. Okay, so we were talking about the power supply design, and about that, this design will need to be improved maybe a bit, because you need to have compensation loops for the stability of the system, and yeah, I'm not happy with this design. It's not it's not good. It's not designed for ceramic capacitors, which is what we are gonna use. So we will need what is called feed-forward capacitors in parallel with the top resistor of the divider bridge, and also maybe change the values here. But this can be quite theoretical and calculate. So yeah, I will need to free up some time to do that and crunch the numbers and write the equations for this. So yeah, if you have experience in designing switching power supplies like such, maybe head out to the M17 Discord in the OpenHT Dev channel and just put a message, and we will get back to you, because it would be interesting. So for the rest of the power supply design, we have this, which is smart button manager, something like that. So you have push button here, which can be used to power the device up, on and off, so basically, as well as send in the interrupts to the device whenever we need to. And this is the logic of the buck converters. Okay. Okay. So yeah, this is for the power supply design. Some components have been selected already, especially the inductors, because you need actually the ESR value of the capacitors and so on for the calculation of the rest of the components. Also the footprints for the inductors tend to be yeah, you don't have like a standard footprint for the inductors, so you need to know that in advance. Okay, so this is the power supply design, and now we will have a look at the FPGA. So the FPGA, it's from Lattice Semiconductors. It's an LIFCL40 in a QFN form factor. We picked QFN, well, QFN was picked before I arrived on the project because it will be better for us and maybe you to toy around with it. Mainly FPGAs come in two main form factors nowadays, BGA and QFN, and well, BGA can be a pain to design but also to play with. It might also heavily increase the cost of the board if you want to manufacture BGA routed FPGA, because if you have a fine pitch device, the manufacturing processes become expensive very, very quickly. So there are two main things that we can see on this schematic. First is a load of capacitors, and then the different modules of the FPGA. So yeah, several banks, you have to pay attention in the datasheet that all the banks do not support 3.3 volts, and all the banks do not support LVDS signals natively, which is what is used to discuss between the FPGA and the transceiver. And so the way that the FPGA will be handled for now is that when we start up the MCU will send the configuration to the FPGA via a slave SPI port, and then the FPGA will start and do its magic. And the FPGA development part, the VHDL part, is done by Wojciech, which is I think in the chat here. So hello Wojciech, if I'm pronouncing your name correctly this time. And so yeah, that's it for the FPGA. A lot of things can be said for the FPGA, but let's keep it short and then go to the PCB to route some tracks. And then yeah, finally the transceiver, which is this one, which is quite nice. It supports from 300 and something megahertz up to about 1 gigahertz, and then another output for the 2.4 gigahertz band. So we have a TCXO, which is basically mandatory if you want some stability in your clock and your frequencies. And then, yeah, the RF output, and right here, and the LVDS signals and SPI signals for the configuration and data exchange between the rest of the system. And so the RF tracks are gonna go through a button because it's differential output, but we need single-ended signals. Then some filter, a switch, and then one antenna. So yeah, that's as easy as we can make it. We have we have no power amplifier yet, because we have to keep the design simple if we want to make some progress, of course. Okay, so this is, and of course, our small logo, which will also be on the PCB. Right, so now maybe switch to the PCB here. So it's, of course, a work in progress, otherwise we wouldn't be here tonight. And yesterday with KC1 Alpha Whiskey Victor, we made some mechanical design to find how we could fit the connectors on the board, because it turns out that ST microelectronics do not give the accurate dimension and location of those connectors. Those four on the left and right, they are the Arduino Uno connector, which is easy enough to do, but if you want to align the mechanical holes and then the extension connector and bring together everything on a single board, which will align perfectly with the nuclear board, then turns out that it's harder to do. So if you're interested, we basically had to open the Altium project file, so replace the connectors with connectors which does have holes and pins on it. The default doesn't. And then finally we were able to perform some measurements and place everything together. And then we did export everything in step files to check if there is no interference, which seems to be all right. So yeah, now the connectors are good and we can place the rest of the system. So yeah, today on Discord we discussed a bit about the speaker, the loudspeaker that we will place, and so it was decided that we would place it on the bottom part of this board, so basically between the MCU and the rest of the system. And we have enough room, I guess, to place it basically about, so here would be nice, because on the board you don't have anything. That would be like right here, and you can see that it seems to be free of components. So yeah, but we will place it on the bottom. So yeah, now it's on the bottom silk screen. So this is the circle where the loudspeaker will be placed. But maybe this, this was the connector for the speaker. So the speaker is basically a round thing with two wires going out of it, and you need to solder the wire here. But I think it might be better if we have SMD pads, so maybe we can go back to the schematic and then change the footprint of this. And so, and have a look at the 3D file. What could we use? Okay, it seems that we don't have any SMD horizontal by default on KiCad, so maybe we would need to design that. Okay, well, let's maybe do a quick footprint for that. so that we will add to the M17 KiCad library, new repository where we will store all our creations. Okay, stop. What the heck? What are you complaining about? Yeah, okay, this. Okay, footprint editor. Hey Manuel, hi, how are you? Okay, maybe we'll do a new library that we will call M17 connectors. Should be good enough. And a new footprint, which we'll call, yeah, let's try to follow the KiCad way of naming it. So it will be something like connectors, pin, yeah, head or socket doesn't matter much. Okay, let's copy this name and use it as a base for the next. So right. Okay, so it will be pin 1x2 pitch. Yeah, we have some room, so let's use 2.54 vertical SMD, so it will be horizontal. And okay, and it will be quite easy. We will have two pads. That's we are gonna make it. Let's see if we do 1x3, 3x1 maybe. That should be easy enough like this. Yeah, sorry for the sound, Casey. It surprised me too. It's way louder than I expected it to be. 3x1, and then okay, maybe we can even do it a bit wider. Yeah, this should be good enough. It's plain connector surface mounts for the wires. So done. We'll just modify the library name so that it is using the correct symbols. Yeah, okay, like this. Perfect. Okay, good. So now we can switch the footprint right here. Okay, like this, and on here we just need to import the changes, and it's good. Perfect. Oh yeah, maybe we need to add a key to this so that we don't mistake pin 1 and pin 2. So yeah, let's do that. Okay, we'll put this right here and like that. Good. And so now we need to update it from the schematic, I guess. No, what doesn't? Oh yeah, update footprint. Okay, perfect. And so yeah, this is basically it for the speaker. So we have room to place it right here, and we will adjust it later on if needed. But for now, let's not spend too much time on this. This is so this is the FPGA, and I will remove the silk screen for now because it's spamming and we can't read anything. And yeah, what are we gonna do today? Yeah, there was this that I wanted to place back around here. So we are not sure of the manufacturer that we are gonna use yet, so let's not spend too much time on the RF signals and so on, because if we need to change the width and so it's gonna be a pain. So we can just route maybe the IOs for today and see where this brings us. I will just put, sorry, so you won't see the schematic as I click on the components here, because it will be on my other screen, sorry. Yeah, turns out that routing PCBs needs a lot of screen real estate. Okay, so this is one of the protection resistors that is used on the data lines, and so this is for master and slave out. So this is gonna be the slave output for the FPGA, so let's keep it close to the FPGA and maybe already start to route the signal. So this will need to go down, so we'll see for that later on. This one like this. IO1, where is it supposed to go? Oh, all the way there. And we have IO1, IO0 and IO1 here. Oh, IO2, 3, 4. And they all need to go to the other side of the board. Sad. Yeah, but we can't place them anywhere else on the FPGA because it's the only 3.3 volt pins that are available. So okay, well, we will deal with it. Just remove that and maybe, okay, yeah, these signals need to go out too. I think I'm gonna need to use smaller vias, so I guess we can use, okay, maybe have a look at classic specifications for 4-layer boards, which would be about 0.2 millimeters drill and 0.2 millimeter ring, so like this, and this will be easier to place, and so we can do this. Okay, and so now this one will be, yeah, okay, it can go out of the pad straight. Good. And this, where does it go? All the way to this test point. Okay, so this is good, so we can just put it right here and then route it later on. Okay, so oh no, this one needs to go there. Okay. It's okay. It was this one. And reduce the size of this too. Maybe just change the default size to something smaller. Oh no, it was in this menu. Okay. Okay, this can go down too. Right, and then maybe this one can go somewhere else. So first step is just basically fanning out the connections, do a first routing, and then we are gonna refine it and pay attention to all kind of issues that can arise with pad routing. Pay attention not to route tracks on split planes and so on. So it's not shown here, but we have it's a 4-layer board, and the second layer it's plain grounds. But that's what is usually done with 4-layer boards. But it's recommended to pay attention not to put vias too close from one another to keep from having large opening in the plane. So what we usually do is keep things like this, so that there is a small sliver of copper between the vias. If we put them too close from one another, then we have one bigger opening, and it's not the best. We try to avoid that. So like this is good. And the third layer is going to be used for the power supply planes, but yeah, we are going to do that later. This is going to cause some issues, I guess, yeah. So maybe this whole thing can go up. like this. This can go up too. Okay, this and use a larger track. Oh no, maybe no track at all. It's gonna be through the plane directly. So this, like that. This one you can. Yeah, we'll see later for that one, but it's so the larger one are 10 microfarad caps. So those can be a bit further away from the FPGA. What's most important is that those small 100 nanofarad one are kept close to the power pins of the FPGA. This is most critical. So now we have more room to route our signals. And so this need to go, yeah, okay, right to the opposite. Yeah, on this side we don't have many signals, but we have all the LVDS pairs which are on the top of the FPGA, and this needs to be facing the transceiver because those are the most critical one, and those needs to be as short and straight as possible. So we are gonna keep them there and keep this component in this orientation. This needs to go down. Okay, so this is easy. Maybe we can even route it in between the capacitors and then down. This needs to go. Oh yeah, this is the jumper that is gonna be used to force the FPGA in JTAG mode. So yeah, we'll put that one wherever we have some room available at the end. It's not critical. It will be just a DC signal anyway, so IOs, IO, and this need to go to the microcontroller too, and yeah, but we have protection resistors here that we still need to place, so let's do that too. So this one is for the push button controller, and yeah, so no, it is gonna be a signal created by the MCU, so let's put it right here. Let's check. Yeah, I have a mechanical keyboard and the mouse. It's an old Corsa mouse, and yeah, I have my mic is like a few tens of centimeters away from me. I don't know if I can improve the setup, but it was done very quickly for tonight, so it's gonna be it for today. Maybe keep an eye on the stream too. Yeah, okay. And this doesn't need to be vibrating so much. Okay. So protection diode for interrupt request from the transceiver. So we are gonna put that about here. And why is this one placed like that? This is better. So this like this. IOs. Yeah, we're just gonna put them about here to save some space. IO2, so this is the RF reset is gonna be generated by the microcontroller. Let's avoid having components too close to the edge of the board, so yeah, here it will be fine. We don't have any signals right here anyway. And this one, it's the done signal, which I think is generated by the FPGA. So right here is good. Okay, we have the programming. Yeah, but this one was placed near the it's one of those like programmings right here. We don't have that many signals here, so maybe it will be better if we have this one right. Come on. Right here, like this is okay, good. So we can now shift this right there and this one there. So clock input. This clock input is generated by the transceiver for the FPGA, and it's 26 megahertz supposedly. It needs to be carefully routed too, but it's the opposite of the transceiver. Maybe we should route that first to avoid. Yeah, so it should take priority with regard to the other I/O signals. So yeah, some components are misaligned, but you can also, so sometimes it's the when you really want to densify the design, you cannot rely on the grid, because you either have to pick a grid which is too fine, which is a bit weird, or you have to use the control key, and then you don't have a magnetism on the grid, and then you can really do so you can misalign things by just a little bit, just enough to be annoying, like this. Yeah. Yeah, but actually, so the way KiCad does the alignment is you can either click on the footprint, which then will align the footprint with respect to the center of it, or you can pick a pad and then it will align the pad. So if you align the pads together, and then yeah, it depends on what is the reference that you pick, but also this one is a resistor and this one is a capacitor, and it's not exactly the same footprint. So I guess you can see that the space in between the pads here is a bit longer on this footprint than on this one. So those two doesn't align very well, but those two should align properly. No, they don't. Oh, nice. I don't know why. Maybe the grid was changed in the meantime for this one. So no, they are aligned correctly. And this one, oh yeah, we can kind of get them aligned, but just not perfectly. Nice. Okay, this is the coupling capacitors that was not placed correctly. It does need to be near one. Which pin does it need to decouple? Either 39 or 29 or 21. So 39, it does have a capacitor. 21 too, so it should be. This one should be it's misplaced. It should be either pin 15 or 46. And it will be pin 46, I guess. Yeah. And so same, this one needs to go higher so that we can put this one closer to the device, like this. Yeah, so can you see actually the dimensioning of the footprint, I guess, is related to the IPC standards, which it's a big group which determines how you should design a footprint with regards to the density of the boards, the size of the components, the type of components, the quantity of solder and the heal that you want on the solder joint and so on. Lots of things that you usually don't do by hand, so you have calculators and scripts. So KiCad does rely on a script that is on another repository on GitLab, something like that, that you can find if you look for it, and then it will generate you footprint. So this QFN footprint, for example, was generated using this script, and I guess it's the same kind of script that generated them. So if you tell it that it's a capacitor, then it's gonna do it a tad bit differently from a resistor and inductor. I don't really know more than that, but yeah, that's the gift of it, the gist of it. So yeah, this, what were we doing? Okay, this needs to go right there then. Okay, this is fine. We don't want it to be too close from the LVDS pairs. So like this should be good enough. We have about, yeah, maybe we can even put this right here. Okay, so we have a bit more clearance right there. So what is recommended is to have about, I think, about twice the width of the track in between other signals and so on. This is a DC signal, so this shouldn't pose too much problems. And in between the pairs you need to have also some distance too, so, and especially if they run parallel to one another, which should be avoided as much as possible. In this case, I think they are gonna run parallel to one another, but we are gonna have we are gonna space them far apart from one another, and then have some ground plane or something like that. So I don't expect that to cause much trouble. So okay, yeah, this is the clock output from the transceiver, and this needs to go down there for the clock input of the FPGA right there. How are we gonna do that? It should be we can route that on the bottom plane, but then we have to pay attention to the power plane. So maybe it's better if we route this. Okay, we are gonna unroute this. It is yeah. This one is an SPI, but this is the SPI for the FPGA. So this is not critical because it's not. Oh no, it is gonna run a lot. So this needs to be taken care of correctly. Okay, first the clock. I guess we can just roughly like this. Should be good. So yeah, this one, if it's far enough from the FPGA, it's not gonna have power plane trouble, so it's gonna be able to be routed properly. with a good reference plane below, so we can do this, and then right here, let's go to the top, and like that. Okay, should be about good. Oh, I don't like it to go below the speaker because it's inductive, and so it's gonna go like this. Yeah, this area should be avoided as much as possible. Yeah, we are gonna move things around later on anyway, so let's not worry too much for that for now. Hi, and Andrzej. Sorry, I'm having trouble pronouncing your name. It's not that common where I live. Welcome on this stream. So we are designing the PCB for the proof of concept for the OpenHT project, which is an open source HT that we are currently designing. And so, yeah, we are routing the IOs in between the FPGA and the headers connected to the MCU. So, programming, where does it need to go? Okay, on top of there. Maybe some of those will need to be reassigned on the header to avoid having them crossing one another too much. So for this, so init, for example, where does it go? No, it's not that one. It does go, okay. Okay, let's start in this order. And then programming needs to go below it. So for now it's good. But I would like to avoid the programming pin running parallel to the clock, so I'm gonna move that. And put this right here where it's not gonna bother us too much. And okay. Then this can go like that, and then run close to this pin. Those are not gonna carry any frequently used signals, so it's not problematic if they're close to one another. Can even go a bit closer than that. Okay, it won't do it. Okay, and this can also be shortened a bit, and this too. Okay. Okay, and then we have the done signal. we are gonna do the same thing. Put the resistors this way, and so those, yeah, we place the resistors close to the MCU, so this one can put it right here. And so this done signal is not gonna be used much. So init and programming and done are used for the programming of the FPGA. So it's gonna wiggle a bit at the beginning and then not much. So we should be good. This needs to go to the bottom, and as long as we don't need any crossing, let's use the top layer, sorry, and like this. Okay, and then we need IO 765. Yeah, we need some place to route them. Let's put that here. Okay, IO 7. Oh, this one needs to go there. All right. Then go to the bottom layer, cross, and maybe we can just stay on that layer for this. Okay, like that. And this one needs to go left too. Good. We are gonna follow the same path. And oh, where are you going? Okay, and then this is in our way. So move. Yeah, that would be good. So the I/O lines, those are the GPIOs that were deemed unused on the FPGA that we decided to route to the MCU in case we need them for some reasons later on. So we will, for example, need one line for an IRQ mechanism so that the transceiver and the FPGA, the MCU and the FPGA can exchange data via the SPI bus at a suitable speed. So this will be routed among the 3 I/O pins. A set of I/O pins will also be able to be reused as an SPI bus if needed, so that we could have 2 SPI bus, one for the configuration and then one for the data exchange. Okay, this need to go up. Is it a bad idea to put vias under the FPGA? I would try to avoid it actually. So yeah, maybe I guess if we put a via right here, it should be good, and then we can route that. this needs to be flipped. This is too high. We can't align those. Maybe I can just at least pick a finer grid from, yeah, like this, and now, oh, this is better. Okay, this is too high. Okay, like this. Okay, good. This one, yeah, it's the one that we don't really care about. So we have 3 more IOs to route right here, but we are getting close to this PI bus, which needs to be routed properly. So let's try to do it well. SSI, SSO, what are those? Those are yeah, those are the data line. We need to pay attention to those one because they are gonna run a lot. So yeah. Maybe unroute the unroute this and that because it's not critical, and also this we can put it further away because we need room for the SPI bus. So now we have this, and we can, okay, this is fanned out enough for now. Is there a way to, okay, TMS, it's a slave select line, so it's not critical. So we can do it like this. This can get closer to the line. And so this frees us some room for the data lines, which are more critical than the other one. So we can do this. Do we have room to place? Oh no, the SSI, the resistor needs to be near the connector, so it's alright. And then we can maybe do via about. Oh, but we will need some ground via for this capacitor too. So this will go up, and this will go move and go here. Will be good. No, maybe we don't even put the VR right now, and just route it down until here. Then it can cross the board to the bottom and then go there, up, and here. And this will also be needed for the JTAG port, but this is probably never gonna be used. or at least not much, so we are gonna route that last. It's not critical. Okay, can we align this? Not really. Oh yeah, and it's also being routed below the speaker, so change that. Maybe we can. Yeah, no, okay. Like this. Okay, good. Oh, I missed the messages in the OpenHT dev channel on Discord, sorry guys. Just reading it quickly. Okay, so yeah, invalid.code. Yes, we could indeed swap the FPGA image when switching modes. This is completely feasible. It would have a few milliseconds of downtime, which is not much, and we have 128 megabits of no DRAM. No, we have a few megabits of flash memory of NOR flash memory on the Nucleo board that we can use to store all the FPGA images. So yeah, I don't know if you are still here. Your message is quite old for now, but yeah, it could be done, but I don't think it's gonna be needed. But the way it's gonna be done is, so anyway, the FPGA is gonna be part of the MCU firmware in a way. So we are gonna need to develop an add-on for the flasher, and then the flasher is gonna load the FPGA image or images in the NOR flash using the MCU, and then flash the MCU, something like that. So people are gonna be able to modify the image of the FPGA very easily. Basically just recompile your project and upload it, which is gonna take a few seconds. We could have a dedicated SPI flash, but it's yeah, we don't need it in this case. Yeah, I see that that's where the discussion was oriented to. Yeah, the hardware design checklist, I checked it already. It was of great help, actually. Yeah, okay. So yeah, I'm gonna stay. So for the Discord guys that use Discord instead of YouTube chat, yeah, I'm gonna stay on the OpenHT dev channel so that we don't spam everybody on the server. Okay, so yeah. Yeah, so it's in moments like this that we are happy that we use the O4 form factor for the capacitors, because if we used 0805, which is this, then yeah, let's forget it. It's way cleaner this way. Okay, so we were routing the SPI bus. This, then down, and then like this. Maybe we can cross to top. Okay, I can't. Why can't I cross? Move. Move. Yeah, okay, go away. Don't need you right now. Okay, and okay, no, we can. Then we can cross the speaker, because we are gonna have ground planes anyway, so shouldn't be too much trouble. Okay, so this is good. Okay, so SPI bus is mostly done. The clock needs to be routed carefully too. Can we done? Okay. IO1, do we have, oh, we don't have space for a via here, so let's create some space. Still not enough. Yeah, but we still don't have room for Can we place vias here? No, we can't. Okay, let's move this big one down, this, and then we will be able to do that. Like right here and right there to ground, so we can put them close. Let's assign them net to ground. Same. Okay. So here we have enough room for the vias everywhere. Good. And we need to route 4 IOs right here. And this one, yeah, still need to find place for a via, otherwise we are not going to be able to use this signal. How do we do that? Like this. This one can go up a bit, so this one can be kept straight. Oh, the sound is way too high. Okay. Okay, good. Alright, so now we have everything we need to route this out of his hole. Come on. Okay. So now this one can go down. Okay, how are we gonna do that? This one needs to go like this. This one like this. And VCC, VCC. Okay, so we are gonna need to put a via here, so I guess it would be better if we could place the capacitor in between the via to the power plane and the pin, but we need to do that for all those. So How should we do that? So this also needs to be routed out and to here, but we are gonna keep it away from the LVDS pairs. It's not gonna be an easy one. Okay, this, yeah, but can we put one more? Yes, we can. Oh, good. Okay. So we can even pull that a bit. Okay, nice. And so we can have maybe at least one via yeah, this. Okay, keep it like that. Then this can be pulled like this. Maybe even like this, so that we have space for vias. We could do it. Nope, not this. I think if we do this, then we can join those two with a thick trace, and also using a thick trace do. Okay, I need to assign a net, of course. Which is VCC, FPGA VCC, okay. And then now, like this. Okay, remove all the small tracks. Okay, this seems nice. Maybe I can, no, okay, let's keep some room for, so we are gonna need vias for those two to get out of there. And this one. Two, okay, great. So it's starting to be a bit crowded, but that's not problem, not a problem. We don't have much more to fan out from there. Yeah, we don't have much more to fan out from the FPGA actually. So yeah, this is the hardest part. Good. Getting thirsty. All right. So we found out the signals. Okay, let's can keep routing the SPI signal, but I will invert those two. What? No, really. And then we can have track on the bottom for this one, which will go. Oh yeah, the clock needs. Yeah, those need to go both to FPGA and transceiver, but we need to get it out. This well, maybe we can just straight down to the MCU connectors. Okay, good. And route this. Okay. All right. Oh, those two signals need to be routed there too. So maybe it would be best to do like this, put it around there, and then route those signals something like this, so we avoid completely the area of the speaker and all those, even though I don't know if it's gonna cause any problem or not, but best to avoid it in doubt. Yeah, okay, roughly where we are gonna want them to be, but not worry too much. We are gonna do that better later on. Just okay, good. And this also like that. I'm gonna group it near the other. So yeah, okay, good. I/O pins, those need to go to the other side of the board. Maybe we can just route them. No, not like this. Those are not critical signals, so we can do it like that, basically. Oh yeah, putting this is a bad idea. Get some space. And yes, and now we can put that there and route the top layer like this. Okay, good. IO1 done. Then IO2. Let's start with IO4. The clock, let's get it further away from there, and like, oh yeah, but we are gonna have loads of vias around there. Okay, like this. So now okay, so this is gonna be a problem. Okay, we are gonna route them until about here, and then we are gonna have to reorder them so that the one which is on this side can get on that side, so that we avoid crossing all of them. It's annoying otherwise. IO3, which is below that one, so maybe we can drop that a bit. So that we have room for this via. Yeah, okay. Maybe we can move that around. Move this around like that. This can be there. So now we can route. No, actually, like this. This can move a bit too. And so we can place this right there, and same path for the signals. And finally this one, which we don't really care about, it's just where are we gonna place this jumper? Yeah, let's put it there for now. And so we will need to get the track around. And oh, we don't have room for the via. So, okay, thank you, window. Come on, okay. Like that, and now should be okay, good. And okay, this will go down. Then that would have been okay, we will see that later on too. This signal needs to go on the other side too, but how? Maybe this is easier if we can get the clock signal to go around like this. Then this can go this way and join the other signals. So this will move, and yeah, okay, perfect. So we have IO1, and IO1 is routed up to there. IO2, this is unrelated. This is yeah, power supply button. We will see where we have to place that too. Do that later on. What is this signal? Yeah, glad to learn you something, Casey. glad you learned. That's the spirit of it. Okay, so how will we do that? This. Okay, so let's have a look at both the schematic and the PCB file together and rename the IOs. This can, okay, and this can go here. Okay, so we want to avoid the signals from crossing, and the IOs are free. We decide where and how we assign them. So let's decide that carefully. This signal, which is on top of all our signals, it will need to go, so it's IO0, and it needs to go as high as possible, and so we are gonna exchange IO0 and IO5. So leave the sheet, connector, IO0, or maybe we'll do that on the FPGA sheet. Can we do that? Oh yeah, it's not very important anyway. IO0 and IO5. Well, I can just rename it actually. IO5 and IO5 will become IO0 for now. Okay, then second one is IO1, which will need to be IO4. So IO4 will become IO1, and IO1 will become IO4. Then IO3 needs to be switched with IO2. And then so we have IO3 and okay, let's cut the net and re-import okay, so now oh no, okay, so this one is okay, it's IO5, okay, good. And so this needs to go way up to here. Okay, so we can remove that and remove this via and this and reroute it up to where it is needed. this can disappear too. Yes, Wachir, you're right. It's better to route tracks to be perpendicular to one another, especially when you have a 2 layers board, because otherwise it's gonna generate crosstalk between the tracks. In the case of the proof of concept, we are gonna use a 4 layers board. So then it's a matter of how tidy your board is gonna be. You can just switch to another layer whenever you want to route in a direction or another. In this case, sometimes you just want to avoid vias in your tracks too. And I try to route as much tracks on the top because it's gonna be just on top of the ground plane, which is gonna be very large, and this is for the return current of the signals that are carried on the lane. So for the SPI bus, as it's gonna be a few megahertz for the clock, if you route this track over a split in the ground plane, it's gonna generate a lot of electromagnetic noise, which you want to avoid. So by routing this on top of the ground plane, then you are not gonna have any problem because the return path is just below the track on the ground plane. It's good. But yes, you can also do vertical and perpendicular on independent layers if you want it. I don't know if you understood that my rant about routing tracks. Let me know if you didn't. Okay, IO5, we were routing that. Let's place the via close to the resistor. Okay, right, like this. Keep them apart from the connector and try to have them aligned too. That would be nice. So like this, it's good. And okay, so this needs to go down like this. Perfect. And this, okay. This can disappear too. No, bottom layer, and yeah, so then we just need to route it down. Okay, this one, and it should, oh yeah, this is the one that is gonna be connected to the jumper. So yeah, we will move that around later on too. This one, oh yeah, let's keep some space around the capacitor below. This one is annoying. Okay, we are gonna remove that, and it's gonna jump between the layers as needed because it's not critical. So now we can route the rest of the IOs. Like that, okay. And this go up and up and up and up. Up to here, where we are gonna put a via and then connect. Okay, and let's align those like so, I think. Yeah, perfect. It's all aligned. I like that. Let's keep this cursor. It's nice. But it needs to go up a bit. Right. Yeah, this is the init and signal, which is already routed, and it's on the top layer, so it's fine. This is one of the slave selects, and this is flipped. Like that. Where does it need to go? Oh, right there. Good. But we have a track in the middle of it. And that's not a problem. We can just swap those two actually. Yeah, let's do that. So delete this, re-import, delete that too. And so now what did... Oh yeah. Oh, did I? Okay, let's swap the resistors too. Oh no, but no, the numbers are not in the correct order. I don't like that. Or maybe I can just... Does it work if I do that? I don't know how KiCad references them. No! Oh, how sad. I just undo that. So. Okay. And so, yeah, okay. We will move that up to here, and this one needs to move down then up to down to here. Hey, why don't I have any names on those pins? Hello. What's your matter, buddy? Okay, perfect. We just swapped them, and now conveniently the routing is much easier. No useless signals crossing and so on. All right. And this can go straight to this. Nice. Good. This one, yeah, I can remove those. And okay, well, nice. This is much cleaner, I like that. And now we have those two signals which are down there and are in the correct order too, which is nice. I can stick them up. Oh no, we don't need a via actually. We can just route that on the bottom layer. Hey, come on. Okay. And last one is, oh, we don't have, okay. We don't have room for this one. It's need it. Okay, make room for your friend. And finally, this one, which can move up to. Like this. Okay, good. So for the IOs, it's mostly done. We will maybe need to okay, see how we can route this one, but we will need to okay, and yeah, this. Yeah, this one is gonna be a bit messy, but who cares? Yeah, it can go down to like this, so we don't need that actually. Okay, this one can maybe move. Can we drag that like this? Good. Okay, nice. We will need to put some silk screen to explain what this thing is doing. Actually, do we need that many test points, given that we already have through holes, headers here? Do we need that? Okay, let's keep them just in case and put them like this. It needs to go here. Yeah, it's gonna serve as a duplicate in case we need to probe or solder wire. It will be done more easily. And this one is right there. Yeah, I mean, we might want to place the transceiver upper. Yeah. We need some space for the. Yeah. So this is the power supply, which, yeah, we could actually shift everything up a bit. It wouldn't hurt, but I like to keep the groups spaced a bit so that we can have place to install a shield later on. So maybe I can just move the transceiver up a bit, which means that the LVDS pairs are gonna be a few millimeters longer, but it's not really an issue. So it would be like that. Okay, what happens if I try to drag all this up a bit? Okay, I can't. How sad. Maybe if I just pick the footprints and the vias too. Can I move everything? No. Oh. Well, let's just. No. Take everything and move it down a bit. Yeah, I think like this it's gonna be good enough. We are just gonna move the TCXO to be wrong key, about there, and so we are gonna have plenty enough room for the RF signals and the RF switches and so on, which we can put in their own little shields if we need. This is gonna be the SMA connector. I wanted to avoid this area because it's gonna have the USB connector of the Nucleo board, so that those two do not interfere. We need to put this one. I think here is the best place, so it corresponds to this place on the Nucleo board, right there. And here we have the buttons, and everywhere else we have like connectors and so on. And I don't know, I prefer to put it there. Like when you look at the Nucleo board, it's gonna be here. It should be. So I don't know what you think about that. Tell me. But yeah, we are talking about a few centimeters of RF track, which is not that much. So we do not have any high power signal yet, so it's not really an issue. Yeah, no, top PCB edge, it's gonna interfere with, it's gonna be too close to the USB port that we might use to power it. And I'm just afraid that once we have the cable, don't you think it's gonna be too many things at the same place? Yes, it's flat, yes indeed. But yeah, I don't know, it's just that one USB cable is already quite annoying, and if we have, yeah, don't know. Also, if you have cables around antennas, I'm afraid that we are gonna distort the radiation pattern of the antenna. So that means that if we have an antenna, we would need to power it from somewhere else. Yes, the SMA thread is outside. Yes, that's, yeah, of course. That doesn't change the... Well, maybe let's discuss this matter later. We still have plenty to do on the PCB. This one we forgot. That. Okay, so also, where are we gonna place the PTT and power button? I picked the same flat one, which is right angled, so a bit like a phone actually. So if we do the same kind of layout as a phone, then we would place the power button, no, yeah, it would be close to the SMA. Don't know if it's a good idea. So it's those are the two buttons. And yeah, so those are the two. So one for the power button and one for the LDO regulator. Yeah, the clock, we can route that up to here, right? So mainly what's left around the FPGA, it's the power and ground tracks and planes and so on. That can be done later. It's not an issue. This can be placed also like this. Yeah, it's yes indeed, the SMA on the side is gonna be like, have you ever held a transceiver in your hands? I don't know. Yes, but also do we really care about that? Who is left on the stream? I see there are 3 people watching, so I guess there is Wojciech. And who else? Casey, are you still there? Oh yeah, you are. Okay. Hello. And do you know who the third person is? Not speaking much. Don't hesitate to ask questions or details and so on. That's also why we are doing this stream, so that we can share that with everybody. If you have some remarks on the way I'm doing things or question on why and so on, don't hesitate. Oh, hello, Rogue Penguin. Hi, welcome. Oh yeah, you may not count as a viewer. Okay. Do I have access to this YouTube console or not? Oh, maybe via the link you gave me. I'll try to open that. Oh no, it's an RTPM link, but this one was used maybe automatically by OBS. Yes, we are chatting here, Mark, on Discord. Yeah, we are splitting the chat between Discord and YouTube, and yeah, that's, I don't know why actually. Oh yeah, the invite in my email. Okay, good. I'm gonna check that. Yeah. Okay. Okay, nice. Maybe I can check if I do a refresh. What do I have access to? Yeah, I never stream, be it on YouTube or any other platform, so I'm not used to that. So what archive you are working out of? What do you mean by archive? Mark. Just gonna wait a few seconds for your answer and check again on to see if I have a way to check the YouTube console or something like that. Studio, maybe? Doesn't seem like it. Yeah. Yes, this is the repository that we are using from GitHub, indeed. It contains the KiCad project, a few explanations on some dimensionings for the power supply and so on. And Wojciech is doing the VHDL part of the FPGA in yet another repository. Yes. Oh yeah, I have to switch account on. Okay. Yeah. Sorry if I make you feel like you are at work and doing support session. Yes. Okay. I can. Okay. Good. I can write in the chat and all. Great. And then it would be oh, and I can see that I have a higher bitrate than needed. Okay, might lower that later for next time maybe. Good. Okay. Well, I will also try to see if I can install a second graphic card in the computer to improve encoding and so on, and so that yeah, we'll test for that too. Okay. Great. Yes, Mark, you're welcome to do that. If you have questions, don't hesitate to ask either. It's no problem. So yeah, my opinion on that is that you have to do it in order to become better at it. It's not my first board, it's not my second either, and so you get some intuitions and some reflexes that come faster when you are used to it. Also, reading a lot of documentation helps. Data sheets often have more information than strictly required, so sometimes they explain a bit how you should do things, but it's more of a general way to do things. You should always pay attention to those details whenever you work with their parts or other parts too. So yeah, and sometimes you have advanced topics that's, yeah, those you don't find details on that very easily, and it can be quite theoretical and so on. So, but those are not strictly required in order to do a board, but if you want to do an advanced board and also pay attention to EMI issues and so on, and EMC issues, then this can become important. But let's be honest, for most hobbyist projects and even most ham radio projects, EMI and EMC is not gonna be very important, so let's not make it harder than it is. Okay, I think we should try to route the LVDS pairs now. And for that, let's first okay, So can we, okay, we will delete that. Yeah, basically, Steve, Casey, the SPI lines, it's not specific to SPI, it's specific to the speed of your signals. So when we talk about speed, we mean frequency really. So the higher the frequency, then the more important it is to do things well. Of course, when you reach RF signals, and then you need to pay attention to impedance matching and so on, but this is still something else. But yeah, the higher the frequency, the more potential for problems it have, let's say. So it can be more sensitive to noise and also generate more noise, which is to be avoided, of course. Okay, so I think spacing them like this is way enough. Maybe let's try to get this one a bit further from, yeah, like this, good. And then delete that, delete that. Okay, so I guess for the LVDS pairs it should be enough. We are gonna put plenty of vias here so that it is referenced to good grounds. So by good ground I mean those are gonna be a few hundred of megahertz, I believe, if I remember correctly. It is DDR, so it means that you are gonna sample the data line on each edge, so falling and rising edge, I think. And so yeah, it can go, so the clock line is gonna be 128 megahertz, I think, and then it will be 250 megahertz for the data line, I guess. And so when you have high frequency, it's gonna create inductive current, eddy currents on the sides, and those, well, if we want the reference on the sides to be stable at a solid 0 volts, then we need to put plenty of vias around, which are gonna be stitching, if you want. So we can maybe do a small example here. So we are gonna create, just for the sake of the example, a ground plane on the top, like this. There is gonna be a ground plane on the top anyway in the end, but yeah, okay, so it's filled automatically. And so let's say that you have, so those, it's a LVDS pairs, so it means that the most coupling in the system is in between those two lines. So you have to put them close to one another at a specific distance with a specific track width, which means that it's gonna be impedance matched from the inside of the transceiver to the inside of the FPGA. It's a 100 ohm differential. Oh, do we need to match the trace length? No, I don't think we need to. But yeah, you're right to say that. I don't. Or do we? Do we? Good catch. Let's check in the datasheet actually. So it's gonna be electrical characteristics, I guess, and then IQ interface. Oh yeah, we need to pay attention. So we have so 200 picoseconds inside a pair, and then 500 picoseconds in between the data and what do they mean by okay, so TD1 it's okay, don't you have any definition for the it won't hurt to match the traces. Yeah, I agree, but it's just to avoid useless work. But you're right, it never hurts. You know what? Let's do that. So let's just to have an idea of how hard we need to work. So we have, let's take a velocity factor of 0.6. So that means that the speed is gonna be speed of light times the velocity factor, and then we have okay, I'm getting lost. We have a maximum of 200 picoseconds times the velocity. Am I doing something wrong? Okay, I'm getting a bit tired. It seems 3.6 centimeters of mismatch? No, it doesn't seem right. Maybe they have... Oh no, no, not that. Where is it? Oh, maybe KiCad have transmission lines. Oh yeah, they have everything needed to do the Okay, periods, frequency. If we do like 200 picoseconds, oh yeah, okay, we have an epsilon r of 4.3. Okay, those are all standard values, but from the manufacturer from which I took the first values, which is Aisler, it's a 4.3 epsilon r, which means that we are going to have a speed of about that much, and so it means that 200 picoseconds corresponds to a distance of 2.89 centimeters, so it's really not a problem actually, and 500 picoseconds is about 10 centimeters. The total distance is not even 10 centimeters, so basically we could route them however we want, and it shouldn't cause any problem. However, let's try to match them, because it's gonna be new for me. I never did that, so I don't know how KiCad handles that. This, how can we see the length of a net? Okay, so target skew. So I guess this. You're welcome for the math. Kind of my day-to-day job, doing math. I hope I wasn't wrong, however, because it's getting late, and yeah. So yeah, those, they are, of course, they are gonna be matched because it's straight, and yeah, it's gonna be matched, not a problem. Can we do this maybe? How does it work? Oh yeah, okay, we can. Oh wow. How funny. I would like. Oh yeah, okay, so this is the target length. How can we measure the length of a net in KiCad? Let's search that. Okay, people are arguing online about how to compute that. Okay, right. So oh yeah, okay, it's here, routed length. So this segment is 14.68 and routed length is 31.7. And so if I select the whole net, no, yeah, okay, the measurement disappears, interesting. And you see that we have less than 7 millimeters of difference in here, and so yeah, it's the longest one. Okay, so maybe we can do that. Length tuning settings, target length, let's have 32 millimeters. And minimum spacing, so we are gonna do 3 widths. Width is 0.9. Okay, so yeah, spacing is already enough. So if we do that, so 32 millimeters. What is okay? So doing this, yeah, I guess it's too. So maybe we can pick a longer length, like 40, and then that brings us to 40.0001. But then it's gonna take so much more space. So let's try to keep that low and avoid taking too much space if not required. So this gonna bring it further. Yeah, we are gonna get back to the ground plane thing later on. Okay, so that's yeah, that's sad. With KiCad, routing differential pairs can be a bit tedious because you cannot drag them as you want and so on. If I move that, it's just breaking the track. Well, okay, come on, like this. That's useless. I just did what. And maybe we can also use smaller. Maybe 0.5 millimeter. And then we can. Okay, and so no, we are gonna do that here, and then this here. So yeah, we are 0.2 millimeters. It's fine, I guess. Like this, and maybe we can reroute a bit this one to get it closer to. So like that, and then insert a few wiggles. So maybe we can take smaller wiggles or larger wiggles. Points. That's. ChatGPT says. Okay, ChatGPT says a lot of things. Let's read that. So, ensure you are using KiCad version 5.1 or later, as earlier versions do not have built-in trace length tuning supports. Yes, that might be true, but we are in KiCad 7 now, so it's good, which is quite new actually. Open your project in KiCad PCB Layout Editor, select the Interactive Router tool. In the Interactive Router settings, in the top toolbar, click on the... Okay, so now it's on the right side. It was in the top toolbar, maybe in an older version, but quite old, I think. Tune length button, length tuning settings in the pop-up window, target length, tuning pattern, spacing and amplitude to control the spacing and height of the meanders. Click OK. No, click on the trace that you want to tune. The tuning pattern will be applied to the trace as you move the cursor. You can tune the trace manually by clicking and dragging the trace while holding the left mouse button. Oh, okay, I didn't know that. To tune multiple traces or differential pairs, select the differential pair option in that. Oh, so we can also use the measure tool, the icon with a ruler and arrow. I didn't know that. Okay. What do you mean, Wojciech? What if we wanted to match the length of data and clock tracks, two pairs? In this case, I decided to match them all together, which is useless actually, because yeah, those two needs to be matched together and those three needs to be matched together. So yes, indeed, maybe we can. I will try. So it seems that we can. Okay, we are supposed. Okay, that's it's okay. It's working, but we are supposed to be able to use the left mouse button to. Yeah, and the skew control is in the nanosecond range. I saw that, so yeah, it's right there. So yeah, I mean, if it's in the nanosecond range, if we use this again and use, like, let's say even 1.9 nanoseconds, so it would be this, and it would be about, no, there should be something wrong. 27 centimeters is, or maybe if you are using cables, then you might want tuning with that much length. I don't know. Oh yeah, this is for the RX, and this is, I guess, for the... Okay, well, we are gonna keep that tidy and it should be good enough. So how can I tune the length more accurately? If I do this, for example. It seems that it's always the same, like it doesn't take my settings into account. Oh, good idea. Let's have a look at the board. It seems like the board doesn't care much, really. I guess those are the, yeah, okay. Yeah, okay. So those would be, I guess, the SATA connectors for the differential pairs. And those would be then the differential pairs themselves. And if we are right, it's yeah. And are they really naked on the PCB? Like there is no solder mask on it? Yeah, but I like the wiggles on the PCB. It's like show off, and you can say, yeah, we had to match the length of the differential pairs. It's a very high-end project, and it was really hard, and so on and so on. So you can pretend that you do very, very difficult things while really you don't. But people do not know that, and they do not need to know. Okay, so the wiggles, yes, it's the very technical, theoretical word for it, the wiggles. Or we could maybe call them small waves, oscillations. But no tuning pattern, this is too high-end. So A min, oh yeah, okay, A min, and so A max we could maybe put like 1 millimeter, and no. Oh, perfect, okay. You know what would be nice? A Discord emoji for the wiggles. That would be fun. I would use it. Yes, the path, but you can, so have a look. If I click on this, I don't know if it's gonna, yeah, you see that I have a tuned length in green, which shows what I have currently. So I know that it's about 35 millimeters. And if I click on the track, you can also see the routed length is 35 points, blah, blah, blah. So right on the bottom. I don't know how good you can see, but yeah. What interface is this? What are you talking about, Rogue Penguin? Which interface? Yeah, I'm not gonna. What would be good would be if we could do round tracks for the differential pairs, but I don't know if KiCad supports that. So how would we need to do? Maybe have a look at the hotkeys. Oh, it would be Control/. Well, doesn't seem like very effective to me. Oh, okay, like this. can I now do that with the differential pairs? Because having them... Oh yeah, what are the differential pairs? Those are LVDS pairs for the data exchange between the FPGA and the transceiver. Nice. Thanks, Steve. Wiggles. Love it. So yeah, those are differential pairs for the LV. So those are the LVDS pairs. LVDS, which stands for low voltage data signaling, I think, if I remember correctly. And so yeah, it carries the, so you can see LVDS TX clock. So this is the clock that the FPGA generates to feed the data to the IQ modem in the transceiver, which is this big thing. So this is the data. This is the clock for the transmit. This is the data for the transmit. This is the data. So no, this is the clock generated by the transceiver for the reception, and this is the data on the 900 megahertz band, or sub-gigahertz band they call it, and then this is the data on the 2.4 gigahertz band. And so the big advantage of having LVDS pairs compared to basically any other single-ended way of doing it is that it's less noisy and less prone to noise, because what is important is the potential of the voltage difference between the lines and not the absolute voltage of the line. So if you take, for example, an SPI bus and you have like a perturbation on the line and the voltage changes at the moment where the MCU samples the line, then it's gonna see a bad sample and it's gonna corrupt your data. Then in this case, if you have an event which happens on the two tracks of the line, then the two tracks are gonna change by roughly the same amount, and so that means that the voltage difference in between the lines is the same, and so it's less prone to external noise, and also it will generate less noise because the electromagnetic fields which takes place, it's just constrained in between the two tracks, which is a very narrow, small thing. So yeah, less prone to noise and generates less noise, also helps in having much higher speed signals. So SPI, you can get up to a few tens of megahertz if you do it right, but this can go up to gigahertz. So PCIe, for example, it's not strictly speaking LVDS pairs, I think, but it's the same idea. It's differential pairs, and so you can go up to very high frequencies, gigahertz, in the gigahertz range. Which, if you're interested, I have somewhere an old project where I designed a PCI Express adapter for the XTRX SDR radio. So if you're interested, just let me know. It doesn't seem like I can do round routing, round corners on the pairs. Sad. How will I do? I don't need wiggles, that many wiggles. Maybe I can just. So this is. Yeah, okay, I will do this one a bit shorter because it doesn't need to be that long. And so now it's 32.13. Let's tell it to do 32 millimeters. Oh, maybe point, yeah, let's do that. And now remove the wiggles and this, route them and tune. And just like that, perfect. Then remove the wiggles here. And tune that one too. It seems that it's having a hard time tuning it to a, let's say, proper length. How can I help it? Oh, just like that. Okay, right, good. We have plenty of room, so we don't need to worry about that. Maybe we can get this line a bit closer. Yeah. It's gonna be tighter in the final board, I guess, but we have the room, so we are just gonna use it. Fillet track. Is it like the real word for it? Fillet track? If it is, then it's not a nice expression. No. Okay, and then oh, no, okay, fillet track you mean for the round tracks. Okay, right click on two segments. Oh, can I... Yeah, good catch. Yes, but... Yeah, you see, it doesn't keep the spacing exactly, and I prefer to keep them like this. This is not a big issue, actually. It's not crazy high-speed signals either. It's less than a gigahertz, so just doing this is enough. I prefer to have them with an angle than not having the correct spacing in between. So yeah, this is better to have a good spacing for to have a consistent impedance along the track. Yeah, okay. So just like this, we have all our tracks. No, maybe I just remove the useless corner here. Like that, and then tune. Like this, okay. Yes, I know, Wachir, we don't need to match them all together, but yeah. It's true that maybe we could match those two and then match those three together so that we avoid useless wiggles. So we need to first check which is the shortest. So this is 30.87, 30.34, 30.0696. So it will be 30.07. And then we can do we can do that. Oh yeah, I need the longest one, of course. Stupid me. So 30.88. And then we can tune like hello, I want to tune it. Oh, I can't. Maybe I can't because why? There is no good reason. Or like this maybe? I need to have shorter wiggles. I can't do that. Interesting. I cannot match it because it is too close to the final length, I guess. So then, so this was 32 point. Let's try with then 31 millimeter and then interesting. No, we need that. So yeah, okay, so we need meh. Okay, let's keep it like this. It's done. It's matched. Just this one I want it to be on the inside so that it doesn't bother the outside too much. And let's put it okay, perfect. So for the LVDS pairs, it's done. I'm soon gonna go to sleep, so maybe we'll just finish with what I started with a few moments ago, explaining what we are gonna do for the ground around the LVDS pairs. So the thing is, basically, from a theoretical point of view, any track is considered as an inductor, basically. And as you know, the main thing that an inductor does is generate magnetic field. And when you have a magnetic field which varies and changes over time, then that's what happens in a transformer. And then it's gonna induce voltages in the conductors around the varying magnetic fields. So this is a track, so this is an inductor if you want, which is gonna have high speed signals, so generate a magnetic field which is gonna vary at a few tens of megahertz, few hundred megahertz, 128 megahertz, I think. And so this is gonna generate a high frequency magnetic field, which is gonna generate eddy current, induced current in the ground plane around. So when you have current flowing through a plane, then you have the current times the resistivity of the plane, and then you have a potential difference which appears. And then suddenly your ground is not 0 volt everywhere as you expect it to be, and it's moving a bit, and then it's moving around your differential pairs, which is gonna, yeah, it's all gonna be messy quite quickly. And so what you do is you take vias and you place them like this around your tracks. Then you have on the second layer this whole green field. It's ground, your reference ground, what you call 0 volts, but the world doesn't care what you call 0 volts, but it is what you call 0 volts. And so with that many vias, trust me, this ground plane is not gonna vary much from the 0 volts that you like. And so yeah, this is how you can do to ensure that the ground is clean around and your signals are referenced to the ground. Because when you design such a line, you take several parameters in account. You account for several parameters. Maybe we can use this to have a look at it. Transmission lines. Coupled microstrip line. Okay. So we are in an odd mode because it's differential, and so which means that when one is high voltage, the other one is low voltage, like high level and low level. We want a target impedance of 100 ohm. We have an epsilon r 4.6. Substrate, okay, tangent, the dissipation factor of the substrate, let's just use default values. Components parameter, the frequency is not gonna matter much for the impedance, but just in case we can put that. And then we can select, so the width, so we have a width of 0.19 and a spacing of 0.18 millimeters. Okay, so we don't use the same, so the values that I picked, it's the one that Eisler advised. You should always pick the one that the manufacturer advises. They know what they do. So they say that it's gonna be 100 ohm. Yeah, so you see that you account for the width of the track, the spacing in between the tracks. You also take into account the height. Yeah, this is maybe what I need to change. It's 0.136, I think. And so, yeah, okay. Where can I put my target impedance? I don't know. If I want, okay, not a number and not a number also. Yeah, so basically you take into account all these parameters, because each track of the differential pair is gonna form a capacitor with respect to the ground. And so your impedance, the impedance of the line is supposed to be 100 ohms, but of course it's not gonna be 100 real resistive ohms. It's characteristic impedance, which is the value of that is, if I remember correctly, equal to the square root of the unit, the inductance per unit length times the capacitance per unit length. So the thinner your track, the higher the inductance, and the closer your track is to the ground, the higher the capacitance. And then with all these parameters, you find all those so that your characteristic impedance is 100 ohms in the case of an LVDS pair. But then that means that if you do not have a correct ground around your tracks, then it is as if you have a capacitor which is varying its voltage. And so that means that you don't have a good reference. So the voltages on your line is not gonna be what it should be. And you can see that we are gonna have problem if we don't have a correct ground. So what we should do is, what we could also do is just do not put any ground near the LVDS pairs and only rely on the ground below it, which is what it's designed to do. But yeah, doing it like this won't hurt. Okay, I hope you could understand me in this read theoretical rant. I'm gonna save that. I'm gonna delete this actually. It's not now. We are not gonna put the grounds now. Okay, so we routed the GPIO signals today. We routed the LVDS pairs. We had some fun with the wiggles and the length tuning, which is great. Yeah, next time I think we are gonna route the rest of the transceiver, maybe the RF signals, and then we will have to do the power. Power can be quite finicky because this needs to be well done too if you want clean power without too much noise and so on. But then again I will show you a few tips and tricks on what to do and how to do it. I see that I have some vias which are too close from one another and I don't like that, so I will fix this right now. Good. And good. Those. Okay. Yeah, those. Oh, it's gonna be a. Maybe I can just. Oh no. Okay. Good. Perfect. This can go right there. Okay. Those are very close to from one another. This is gonna be a pain. No, okay, it's good. Perfect. Great. Let's keep it there. Yes, I can end the stream, Casey. Watch it. It's 100 ohms for the LVDS pairs, but it's 50 ohms for the RF differential. But those pairs are so short that we don't really care too much about it. But this should be the dimensions needed to make it 50 ohms differential. But yeah, we will see that tomorrow, I guess, or later. I don't know. Yeah, I should have time tomorrow for maybe a new stream. Okay, save that, git kraken, and let's push those changes. Oh no, I can do that. I just first need to Yeah, bedtime for both of us, indeed. Okay. Can I just copy that? Yes, please. Like this, push, and then update the library. And then we had this. Oh no, I did things in the wrong order. I first need to put this with this like that, then okay, yeah, then it's okay. And then and push. Okay. Well, thank you everybody for being here tonight. It was nice to have people around. Now I think it's time to say goodbye and go to sleep. We will tell you more about the next streams that we are gonna do. Just monitor maybe Twitter and Discord, I guess, are the main channels through which we are gonna communicate about that. And see you next time. Bye bye.